Notes 5.1, estimating with finite sums, also called Riemann sums. So, approximating an area with rectangles is called rectangular approximation method. Okay, there are three ways to approximate an area with rectangles. There's LRAM, which means to the left. There's RRAM, which means you're using the value from the right. And then there's MRAM, which means you're finding the midpoint. Okay, so you might see me write these as LRAM, or you might just hear me say the left Riemann sum, the right, or the middle. So our problem is the area of the shaded region bounded by y equals x squared plus 2 and the x-axis on the interval from -2 to 4 can be approximated by partitioning the area into vertical strips. A rectangle is drawn in each subinterval. So what we're going to do should look similar to the third strategy that you all used today during the tasks. So the left RAM, or the left Riemann sum, uses the height of the rectangles determined at the left endpoint of each subinterval. So in our picture, we have three subintervals. And they're all equidistant apart. So this subinterval is a distance of 2 units, this subinterval is a distance of 2 units, and this subinterval is a distance of 2 units. When we say that the height is determined by the left endpoint of each subinterval, we mean that if my subinterval goes from -2 to 0, then I'm going to be using the value at -2 to figure out the height of this rectangle. Okay, so I know my base of the rectangle is 2. That's the interval. That's how far apart my interval is. My height, I'm just going to plug in that left endpoint into the equation, which is y equals x squared plus 2. So we have -2 squared plus 2, which is equal to 6. So the height of this rectangle is 6. So then the area, right, is base times height. So we have 2 times 6, which is 12. And then we'll do the same for all of the other rectangles. So my second rectangle is within the subinterval of 0 to 2. So we're going to do 0 to 2. The base of that rectangle is still 2. The height is going to be, we're going to use 0 as our x value and plug that in. So we have 0 squared plus 2, which is 2. And then our area, base times height, which is 4. And then our last subinterval goes from 2 to 4. That difference is 2, so my base is 2. And I'm going to use that left-hand number to find my height. So we have 2 squared plus 2, which equals 6. So we have 2 times 6, which equals 12. So my total area is 12 plus 4 plus 12, which equals 28. Okay. So this is an estimation. And if we look at all the space that's still left out that we did not calculate, we can see that this estimation is a low approximation. Right, there's a lot of area that we did not account for when we drew those rectangles. So we're going to look at the same problem now from the right Riemann sum frame. So now the height of our triangles are determined by the right-hand endpoint. We still have the same subintervals. So we're still going to go from -2 to 0, 0 to 2, and 2 to 4. And our bases are all still 2. It's just a matter of now finding our new heights. So we're looking at the right endpoint, so we're going to start with 0. So we'll have 0 squared plus 2, which is 2. So my area for this first rectangle would be 2 times 2, which is 4. For our second subinterval, we're looking at our value of x being 2, so we have 2 squared plus 2. So we have 6. So our area is 2 times 6, which is 12. And our last rectangle, this big one here, that right endpoint is 4, so we'll do 4 squared plus 2, which equals 18. So we have 2 times 18, which equals 36. So our total area is 4 plus 12 plus 36, which equals 52. Now if we look at this graph and these rectangles, we can see that we are overestimating by a good chunk here, right? Our graph is this line, this curve, and all of this space up here we're accounting for that is not under our curve. So this is considered a high approximation. So our left Riemann sum for this example gave us a low approximation, and our right Riemann sum for this particular example gave us a high approximation. Now let's look at our midpoint Riemann sum. So now the height of these rectangles is determined by the midpoint of each subinterval. So we still are looking at the same subintervals, right? 2 to 0, negative 2 to 0, excuse me. 0 to 2, and 2 to 4. Those distances are still 2 units apart, so our base is still 2. The difference here is that the height of our rectangles is going to be the midpoint between our 2 endpoints of our subinterval. So if we look here, the midpoint between -2 and 0 is -1. So we're going to plug in -1 into our equation. And that will give us 3. So our area for this first rectangle is going to be 2 times 3, which is 6. The midpoint between 0 and 2 is 1, so we'll use that in our equation. So our midpoint is, our area again will be 6. The midpoint between 2 and 4 is 3, so we'll use that, and we'll get 11. So 2 times 11 is 22. So our total area is 6 plus 6 plus 22, which is equal to 34. So if we look at our rectangles, we see that for each rectangle there's some space that's unaccounted for and space that is over accounted for, right? So there's space under the curve that we're not counting, but there's also space over the curve that we are counting. And so those pretty much balance each other out. And so the midpoint Riemann sum is actually going to give us the most accurate, or the closest area under the curve when looking at rectangles. So the midpoint Riemann sum gives us the most accurate area under the curve. Now let's look at the same example but using 6 rectangles. So now we have 6 subintervals. We're still going to go from -2 to 4, so that's already 1, 2, 3, 4, 5, 6 spaces. So each subinterval, then, if we have 6 spaces and we want to use 6 rectangles, then each rectangle will be 1 unit apart. So that'll be 1, that'll be 1, so on and so forth. So the base of each rectangle will all be 1. And our subintervals will go from -2 to -1, -1 to 0, 0 to 1, 1 to 2, 2 to 3, and 3 to 4. And since we're using the left-hand Riemann sum, we're going to look at that left endpoint to find our height. So we want -2 squared plus 2, which we know is 6. So the area will be 6. So 1 times 6 is 6. Then we have -1 squared plus 2, which will give us 3. So our area is 3. And we have 0 squared plus 2, which gives 2. So the area is 2. And we'll just keep going. So 1 squared plus 2 is 3. 2 squared plus 2 equals 6. And 3 squared plus 2 equals 11. So our total area will be 6 plus 3 plus 2 plus 3 plus 6 plus 11 gives us 31. So looking at the space in here, there's still more space unaccounted for than over accounted for, so this is still under or a low approximation. Right, and the more rectangles we use, the closer we get to a more accurate area under the curve. So if you see we use 12 rectangles here, we get an area of 33.25. When we split this into 24 rectangles, we get an area of 34.56. And this area is actually a lot closer to the midpoint Riemann sum that we used, and we only had to use 3 rectangles for that. So if you look on the next page, it says the following estimates can be obtained for the area of the region bounded by x squared plus 2 in the x-axis on the interval -2 to 4. So this is still the same graph that we've been looking at. Now we're just looking at various numbers of triangles, and we're looking at both the left, the middle, and the right Riemann sum. So when there's 10 triangles, these are the different areas, so on and so forth. So when we have 1,000 triangles, the left Riemann sum is 34.964036. The middle is 35.999982. And the right is 36.036036. So knowing that on this graph, specifically when we looked at those problems earlier, we know that the right is an overestimation, we know that the left is an underestimation, and we know that the medium is closest to accurate. So if we wanted to think of the exact area of the region, then we'd look to see, looking at that middle Riemann sum, we know that it is approximately 36, right? The right is going to be over just a bit. It's over just a bit. The left is going to be under just a bit. So we can estimate that the exact area of the region is going to be approximately 36 units squared. So when we have circumscribed rectangles, or rectangles that go above the curve, that leads to an over approximation. Right, because all of this area that we're taking into account isn't even under our curve, so this will be an over approximation. When we have inscribed rectangles, or rectangles that all lie below the curve, that'll lead to an under approximation because of all of the area that is not taken into account. So all of this space here will not be taken into account, and so our approximation will be under the exact area. Now let's use these Riemann sums on tables. So this is an example from the 2013 AP exam. Hot water is dripping through a coffee maker, filling a large cup with coffee. The amount of coffee in the cup at time t, when t is between 0 and 6, is given by the differential function c. Selected values of c of t are given in the table below. Use the midpoint sum of 3 subintervals of equal length to approximate. So this symbol is called the integral symbol. Okay, and in this case, we're looking to find what would that area under the curve be from when x is 0 to when x is 6. So our interval goes from 0 to 6. So in order to do this, we need to first figure out what are our subintervals going to look like. We want 3 subintervals, and right now our interval is 6 units long, right? To get from 0 to 6, that's 6 units. So we have 6 units, we want 3 subintervals, so each subinterval is going to be 2 units long. So if we look at our table, 0 to 2 is one subinterval, 2 to 4 will be another, 4 to 6 will be another. So if we make a quick chart, interval, base, height, area, we know that our first subinterval goes from 0 to 2. And we want to use the midpoint sum. So we want the midpoint between 0 and 2 to help us find our height. So our base, we know each base is 2 units long, so our base is 2. And our height, the midpoint between 0 and 2, is 1. So we'll look for C of 1, which is 5.3. So our area will be 2 times 5.3, which is 10.6. Our next subinterval goes from 2 to 4, again with a base of 2. The number between 2 and 4 is 3, so our height is 11.2, and our area will be 2 times 11.2, which is 22.4. And our last subinterval goes from 4 to 6. Again, base of 2. And the number between 4 and 6 is 5. So our height is 13.8. So 2 times 13.8 is 27.6. So our total area is 10.6 plus 22.4 plus 27.6, which is 60.6, approximately. Now we're going to do something very similar to this last problem. So here, a speedboat travels downstream on a river. Its speed at certain times is given in the table below. We want to use a left Riemann sum to approximate the total distance traveled by the speedboat from t equals 0.5 to t equals 3. It doesn't tell us what it wants our intervals to be, so we're just going to use the table to figure that out. So our table starts at t equals 0, but we want the distance from t equals 0.5 to t equals 3. So we want 0.5 to 3. So t equals 0 is not going to help us find that. So looking at what we have left, we have 1, 2, 3, 4, 5, 6. 6 values. Each of them are 0.5 units away from each other. So we have 1, 2, 3, 4, 5 subintervals. Okay, so what I want you to do is try this problem on your own, and your final answer should be 56 miles. Okay, do not forget that you're using the left Riemann sum. You're not using the midpoint Riemann sum or the right, you're using the left. So make sure you're using the right value to find your height. Okay, and your distance between intervals is 0.5. So try that problem, and we will check in tomorrow if anybody has any questions.